Okay, we've already seen that we can have limits where the graph is going to infinity or negative infinity, and we've also looked at finding limits as x approaches infinity or negative infinity. So we're going to keep on with that, continuing our look towards infinity. So we have two rational functions. Let's consider first when we have limits as x approaches some a, and let's say a is a real number. What are some possibilities? Well, of course, we could have a limit where it actually goes to a real number. But when the limit as x approaches a of f of x or whatever is infinity or negative infinity, what does that mean? Well, this means we have a vertical asymptote. So we'll look at some examples. So if we take f of x and we see what the limit is as x approaches 2 from the left, here's f of x. Here's 2. So if we're coming in from the left, the graph is going down to negative infinity. If we take the same graph and see what happens when x approaches 2 from the right, here's 2. Coming in from the right, the graph goes up. And notice that means we have a vertical asymptote at 2. So I'm going to make a note here. We have a vertical asymptote at x equals 2. Let's check g of x. What if we look at g of x, which is the other graph, as x approaches negative 1? So here's our pretty g of x. Here's negative 1. As we come in, so here's the graph. As it approaches negative 1, it's going down. As it approaches negative 1 from the right, it goes up. And notice on the graph, we do have a vertical asymptote there. Now, conversely, when we're looking at limits at infinity, this is a limit as x approaches infinity or negative infinity. Instead of looking at it approaching a number, we're looking at infinity or negative infinity. And this tells us about the end behavior of the graph, or of the function. And there's a lot of different things that can happen at the end of a graph. So let's look at it. So we'll start with the first graph, f of x, as x approaches positive infinity. So as x gets bigger and bigger and bigger, what's the right side of the graph doing? Well, it's going down and leveling off at that horizontal asymptote of 2. As x approaches negative infinity, the graph also approaches that horizontal asymptote of 2. So the end behavior of this graph is that there is a horizontal asymptote at y equals 2. On the other one, g of x, as x approaches positive infinity, this one is going up. Notice that we keep going up and up and up. Now, this one does have what is called a slant asymptote. It's also a boundary line that the graph will never cross, but it's not horizontally like leveling off. It's just going to keep going up and up and up. The left side is going to keep going down and down and down. So it gives us that end behavior of the graph. Now, there must be an analytical procedure so that we can figure out these limits at infinity for the times when we don't have a calculator. Now, hopefully you've spent a lot of time thinking about end behavior in some of your previous courses. So let's see what we've got here. The first one is x cubed, so it's odd, and the leading coefficient is negative. So let's remember some of these things. If it had been a positive x cubed, it would go Egyptian style up. Negative x cubed goes down. So what I would say on this one is as x approaches positive infinity, the limit's going to go negative because, how do I want to word it? The degree is odd. Leading coefficient is less than 0, so it falls to the right. The other way you can look at it, if you didn't memorize the behavior of graphs in your previous courses, is as x gets really, 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 really big, like a billion, is subtracting 4 going to make a difference? Is adding x going to make a difference? Not really. We're really going to be looking at this x cubed, which if I take a billion and cube it, it's going to be really, really, really big. And then if I make it negative, it's going to be negative really, really, really big. So negative infinity. The next one, how could we look at that one since it's not multiplied all out? Well, we can still figure out the degree. So we have a negative x, but it's being squared, so that's a negative x and another negative x. This is a positive x times a positive x. If I multiplied all that together, I'd get an x to the 4th. So I've got an even degree, and the leading coefficient would be positive if I multiplied everything out. So even degree acts like x squared. Positive would go up and maybe do something and then go up. So it's going to rise to both sides. So the graph rises to the left and right. So if I'm looking at what's happening to negative infinity, it's going to go to positive infinity. So the next one is a horizontal, rational function which could have a horizontal asymptote. So the way I like to look at it is, again, if we're thinking about a really, really, really big number, the other numbers, like the constants, aren't going to matter. We're really going to be looking at the negative 2x and the x. They're the same degree. So same degree. In numerator and denominator. So there is a horizontal asymptote. At y equals negative 2. Now there's a way to do that pretty fast too, but let's think about more of these rational functions. Here's 2 more. One of them's 3 over x and one's 1 over x squared. What do we notice about each of these? Well, okay, so the numerator is some constant. The denominator has the power of x. And what do they have in common on the graphs? Well, they have a horizontal asymptote at y equals 0. And they actually both have a vertical asymptote at x equals 0. That's nifty. Wonder if there's anything that could help us figure that out. So we're going to look at finding horizontal asymptotes and all that, and or whether they end up being a slant asymptote. In Algebra 2 or Advanced Math, you probably looked at some rules about dividing the leading terms and figuring out the horizontal asymptote that way, which is, it actually is the way. But why does that work? Well, we're going to use limits to kind of prove this idea. So what we're going to do is take the biggest power of x and divide everything by it. So x squared is the biggest one. So on this problem, I'm going to take the limit as x approaches infinity, divide every single term. X over x squared plus 2 over x squared, x squared over x squared plus 5x over x squared plus 6 over x squared. And let's simplify. Can divide an x, so I get 1 over x. That can't be simplified. That becomes a 1. That becomes 5 over x plus 6 over x squared. Now what happens when I let x go to infinity? Well, anything that had a constant over a variable is going to go to 0. So I end up with 0 plus 0 over 1 plus 0 plus 0. So I end up with 0 over 1, which is 0. Does that match what we have in the graph? Horizontal asymptote at 0. Cool. Let's do it again. The limit as x approaches infinity of the largest power is x squared. So I'm going to take each term and divide by x squared. I'm going to simplify. So that's going to be a 2 plus 7 over x plus 6 over x squared. Denominator 1 plus 5 over x plus 6 over x squared. When I let x approach infinity, all the ones with an x in the denominator become zeros. So I'm left with 2 over 1, which is 2. Horizontal asymptote is at 2. Now the shortcut was, if you take the ones with the largest power, that's a 2 divided by 1. Last one. So divide by x squared. Divide by the largest power in the denominator. It'll make a difference. Trust me. Now let's simplify. The limit as x approaches infinity of x plus 3 plus 2 over x, 1 minus 1 over x. Now when I let x approach infinity, this goes to 0, this goes to 0. Left with infinity plus 3, which is infinity. And notice that on the right side it does go to infinity. So let's see what would happen if our limit at infinity approached negative infinity. Okay, so the largest power in the denominator is x squared. So 2x squared divided by x squared, 7x divided by x squared, 6 over x squared over x squared, simplify, I get 2 plus 7 over x plus 6 over x squared, 1 plus 5 over x plus 6 over x squared. And when I let x even go to negative infinity, these all still turn into 0. So I'm still left with 2. Notice on a horizontal asymptote that both sides approach the same number. Divide by the largest power of the denominator, which is x. So x squared over x plus 3x over x plus 2 over x over x minus 1 over x. Simplify. X plus 3 plus 2 over x, 1 minus 1 over x. When I let x go to negative infinity, I'll have negative infinity plus 3 plus 0 over 1 minus 0. So that's going to negative infinity. So thinking about this, what does it make a difference about whether we're going to positive infinity or negative infinity? Well, it makes no difference if we have a horizontal asymptote, only if we have where the power in the numerator is different than the power in the denominator. Suppose the following were given to you in multiple choice. What would the result of the limit be without really doing any work? So if I look at this one, I notice that the degrees are the same. If I divided out everything by x squared, I'd be left with the coefficients of those terms. So it'd be negative 2/3. This one is bigger in the top, so what would I be left with? Well, if I was dividing it out and everything, this would be dividing into that, which would be a negative, but then that's negative, so it turns it into a positive. What about one that's really weird? Oh, this has got asymptotes and weird things. We've got a graph crossing an asymptote, which is supposed to be a no-no. A lot of stuff going on, but can we still figure out how to answer the question? Well, I'm looking for the limit as x approaches negative infinity. So as x approaches negative infinity, would be down here. And notice it's hugging that horizontal asymptote. This is going to -2. Going to positive infinity is this side, and it's going to +2. Could we do that same problem algebraically? Well, let's think. The square root of x squared is actually just x. So I'd really be dividing everything by x. But underneath the square root, that'd still be a x squared. And that would be the limit as x approaches infinity of 2 minus 2 over x, square root of 1 plus 1 over x squared. And so that goes to 0, and that goes to 0, so that goes to 2. That still works. So when we look at the negative infinity, what we're going to do is instead divide by negative x. Now under the square root, it goes back to being x squared. That'd be a -2 minus 2, well, that'd be plus 2 over x. 1 plus 1 over x squared. Let x go to negative infinity, so all those go to 0. And we get -2. Notice it matches what we found on the graphs. So square root of x squared would be x, but we're looking at negative infinity. So I would divide by negative x. Under the square root, it's still squared. Whoops, that looks messy. So I would get the limit as x approaches negative infinity, -3 plus 2 over x, square root of 2 plus 1 over x squared. That becomes -3 plus 0 over the square root of 2 plus 0, which is -3 over the square root of 2. Limit as x approaches negative infinity, so I'm going to divide by the square root of x squared being -x. And the reason we learn these, and I hate to call them tricks, but techniques, a better word, is it makes it go faster, believe it or not, when you don't have a calculator. So the times you're on the non-calculator portion of the test, you don't have that luxury of being able to look at the graph. So we need ways to get around that. Now this one was an interesting one, because what happens when I let x go to negative infinity. I'm going to have negative infinity minus 2 over the square root of 3 plus 0. So that one's basically going to go to positive infinity.